My name is Damir Zenunović. I'm a professor at the University of Tuzla, Civil Engineering Departments, and my research is focused on concrete structures behavior and environmental impact on concrete structures. I will present you some case studies for evaluation the behavior of bridges by measuring ambient vibration realized by our department. This presentation is an integral part of K-Force Erasmus project with the aim to present methodology for assessing the state or condition of concrete structures. So let's start.
The title of presentation is a System Identification of Bridges using Ambient Vibration Measurements and Numerical Simulations. Bridges are some of the most critical components of transportation infrastructure systems. For these structures, failure is defined as any interruption of pedestrian or vehicular traffic across or under them due to structural distress. Direct consequences of failure can range from injury to loss of life and property in the case of collapse, and indirect consequences such as disruption to economic activities and reduced access to emergency facilities in the event of collapse or closure. Bridges are large and expensive structures that are of great importance to our economy and society. They are often exposed to adverse environmental and weather conditions, and because of that, a maintaining of bridges is very important. Health monitoring and identification of structural modes of bridges is a major component of system maintenance. According to existing regulations, compliance of structure's performance in real with the design structure performance defines with bridge test load, static and dynamic test load. However, loading on the bridge is often expensive. It is necessary to consider that traffic interruption during bridge test, even occasionally, can have significant consequences because the bridges are often the vital point in the transport network. So because of that, techniques based on ambient vibration recordings have become a popular tool for characterizing the system seismic response and state of health of strategic civil infrastructure. I will present 3 case studies with ambient vibration measurements used for determination of real modes of bridge structure oscillation and update of numerical models of selected bridge structures. The first case study is the bridge over River Bosnia in Sarajevo. The bridge over the River Bosnia is a 45 years old bridge located on the route M5, section Lashva Stup. Its overall length is 170 meters and comprises of 2 spans of 21 meter and 3 spans of 25 meter. Width of the bridge is 10.4 meter. Each span is built with 4 precast post-tensioned I-beams of 1.3 meter height with recessed deck. The 5 spans of the deck are interconnected through a 16 cm thick continuity slab over the piers. The superstructure is supported by rectangular laminated elastomeric bearings and at the 2 abutments, marked in the figure with 1 and 6 and 4 piers marked 2, 3, 4 and 5. The bridge is instrumented for ambient vibration test. Measurements were made without traffic interruption. On this slide, arrangement of measuring points is shown. Ambient vibration test was made with 5 triaxial geophone sensors. One sensor was used for the reference point, stationary point 6R, while the remaining 4 sensors moved to individual measuring points 1 to 17 according to the arrangement. Ambient vibration measurements were performed using Instantel BlastMate Pro 4 vibration monitor with sample rate 1024 to 16,384 samples per second per channel. The triaxial geophone sensors used had range of measurements up to 254 mm per second with resolution 0.127 mm per second or 0.0159 mm per second with accuracy plus minus 5% or 0.5 mm per second. Frequency range is from 0 to 315 Hz. The recording system has start common trigger capabilities to enable synchronized data acquisition. During all tests, normal traffic flow was permitted. Testing started in the right lane, points 1R to 11R. Each setup yielded 3 base channels, points 6R, and 12 movable channels. The ambient vibration was simultaneously recorded for 120 seconds, resulting in approximately 500,000 data points per data set. This slide shows the measurements at the base station 6R. Ambient vibration testing procedure consists of real-time recording of the vibrations and processing of the records by means of the fast Fourier transform and obtaining of Fourier amplitude spectra. The peaks of the amplitude spectrum occur at the predominant frequencies of the time function xt, which due to the flat spectrum of the excitation represent the natural frequencies of the structure. The sensors installed along the deck and at the bottom of the abutments and the piers recorded the bridge response and velocity time histories with 120 second recording time. Then frequency spectrum were obtained by using the FFT. Here is presented example of one measurement on base station 6R and one measurement on movable station 4R. On this slide, comparison of vertical channels for measurement setup 1 is presented. The dominant frequencies measured at measuring points are given in table. The dominant frequencies of vibration of the superstructure measuring points, except for a few results, are in range from 3.81 to 7.95 Hz, depending on position of the measuring point over the support or in the middle of the field. The obtained results of measurements, dominant frequencies, are within the limits of test results on similar concrete bridges. There is difference between the dominant frequency of vibration abutments and piers on either coast, which will be the subject to further analysis by defining the soil-structure interaction. The software Artemis Extractor was used to perform the modal identification of the structure. Before procedure of modal identification, it is important to validate all channels. Two techniques were used to perform the modal identification: the frequency domain decomposition and the stochastic subspace identification. The frequency domain decomposition, the first technique, consists on performing an approximate decomposition of the system response into a set of independent single degree of freedom systems for each mode. The singular values are estimates of the spectral density of the single degree of freedom systems, and the singular vectors are estimates of the mode shapes. The enhanced frequency domain decomposition feature offered by Artemis adds a modal estimation layer to the frequency domain decomposition editor. When the frequency domain decomposition analysis is completed and the mode shapes are identified, the enhanced frequency domain decomposition identifies the single degree of freedom Bell functions, and from this single degree of freedom spectral bells, all modal parameters are estimated. The damping ratio can be also obtained. The second, stochastic subspace identification technique, consists of fitting a parametric model to the raw time series data collected by the sensors. Using a specific representation of the transfer function, all the modal parameters are exposed. Therefore, the natural frequencies, damping ratios, and mode shapes can be extracted. The unweighted principal component algorithm was used to analyze the data. Here is presented average of autospectral densities. And on the next slide, stabilization diagram of estimated state space model of the first test setup attained from vibration signals using the enhanced frequency domain decomposition and the stochastic subspace identification methods. On this slide, natural frequencies and the damping ratios obtained from the test setup are presented. For procedure of determination of mode shapes, data from Artemis can be transferred as an ASCII file. On this slide, one example of data list is presented. The finite element models were created using SAP 2000 based on the geometrical and material properties that were used for design, prediction of material properties after 45 years service life, and on the preliminary soil investigation. The first set of models, called SNBM1, is a final element method with different soil stiffness, designed neoprene bearings stiffness and designed strength of concrete. The second, called SNB1M2, is finite element model with designed neoprene bearings stiffness and theoretically predicted strengthening of concrete during service life. And the third and the fourth, called SNB2 and SNB3, are finite element model with increased neoprene bearing stiffness and theoretically predicted strengthening of concrete during service life. The deck was modeled as a shell element and girders as elastic beam elements, as this approach provides effective stiffness and mass distribution characteristics of the bridge. The bridge superstructure itself is expected to remain essentially elastic during earthquake ground motions. Dimensions of neoprene bearings are 300 by 400 by 100 mm, and neoprene bearings are modeled with vertical and horizontal springs. Soil was modeled in two ways. Soil model with the linear springs used for the structure-soil interaction in model S1 to S4, and the second, layered soil model with the solid elements, model S5 and S6, module E determined by preliminary geophysics soil measurements, was used for the solid elements. The foundation structure was also modeled using solid elements, so that the soil foundation contact has been realized by identically arranged nodes of the solid soil elements and the foundation structure. Review of the models is presented in the table. Since the scope of the research was to validate the modeling assumption made and to identify their relative impact on the numerically predicted structural response, the developed finite element models were assessed comparatively. Through this procedure, longitudinal, transversal, bending and torsional modes were identified, whose modal frequencies are summarized in the table. The first comparison was made between modal frequencies of the model S2 and B1 M1 and ambient vibration modal frequencies. In general, it is observed that the modes measured via ambient vibrations are on average 44% higher than those predicted by the model S2 and B1 M1. The real structure is identified as significantly stiffer than predicted using the S2 and B1 M1 model. A second comparison was made between the models with a different soil stiffness S1 to S6 in order to quantify the importance of soil compliance on the predicted dynamic characteristics of the structure. The refined consideration of soil flexibility leads to significant lower values of longitudinal, transversal and torsional modal frequencies, while the reduction of bending modal frequencies is not significant. Through comparison of the S2 and B1 M1 model and the S3 and B1 M1 model, the longitudinal mode is found 8% more flexible the transverse mode 40% more flexible and the torsional mode 5%. The reduction of bending modal frequencies is not significant. Since the finite element models used were refined as much as possible, the model-induced uncertainty can be deemed as relatively low. As a result, the deviations between identified and numerically predicted modal frequencies can be attributed primarily to the uncertainty in the material properties, which seem to be a key parameter for the reliable estimate of dynamic characteristics of structure. In order to improve the convergency, sequential parametric analysis was conducted. The idea was to gradually modify specific structural parameters through a step-by-step parametric analysis sham until a nearly optimal fit was achieved. The results of this parametric analysis resulted in the combination of updated structural parameters with a different neoprene bearing stiffness and concrete strength of structural elements. The results presented in the table show the improvement of the modal frequencies predicted by the models S1 NB2M2, S1 NB3M2, and S5 NB3M2 compared to the model frequencies predicted by S2 NB1M1 model. By comparing the model frequencies predicted by the mentioned models, it is clear that the Young models of elasticity for the bearings, the deck and the piers had to be significantly increased compared to the values assumed in the initial design. This can be clearly attributed to the low deformation strain levels that are developed under ambient vibrations, at which the bearing stiffness is significantly higher than that assumed during design. Also, the effect of concrete strengthening during service life has to be considered. For comparison of the model parameters identified by ambient vibration tests and mathematical models, two finite element models named AM1 and AM2 were selected. AM1 is selected model S1 NB1M2 and AM2 is S5 NB3M2. The comparison is made for the first transverse and first vertical modes. Here is presented experimentally and mathematically identified modal frequencies and mode shapes for first vertical modes. And on this slide is presented mode shapes for first transverse modes. There is a good agreement between vertical mode shapes obtained by ambient vibration measurements and by AM models. The deviations between the experimentally identified and mathematically predicted first transverse mode shapes can be attributed partially to uncertainty in the material properties of structural elements and neoprene bearings after 45-year service. But also deviations could be partially due to unexpected channel errors, which will be studied in further research. Based to the study, it can be seen that ambient vibration measurement can be used to assess the dynamic properties of older existing bridges. The second case study is the twin bridge Goce-Delchev in Skopje, Macedonia. The twin bridge Goce-Delchev is pre-stressed girder bridge with multi-box cross-section. Total length of the bridge is 136 meters, with 3 spans, 24 plus 88 plus 24. The main supports are middle piers and counterweighted at the ends of the bridge. The bridge is a very complex structure. During the serviceability period of about 40 years, several revitalization works have been done in order to improve the structural conditions of the bridge. Based on structural state diagnosis, an appropriate bridge revitalization concept has been selected and realized. The generated experimental results from the ambient vibration tests were very important in verification of the formulated mathematical models and reanalysis of the bridge seismic safety. On this slide, arrangement of measuring points is shown. Arrangement of measuring points is the same for both bridges. One point R16, is selected for stationary station. 2 measuring points are selected outside both ends of both bridges, points numbers 37, 38, 39 and 40. 2 measuring points are selected at the bottom of the 2 middle piers of each bridge, points number 41 and 42. Bridge measuring points from number 1 up to number 36 are distributed in 2 lines at longitudinal distance of 8 meters. The table shows the different stations distribution of each setup. The traffic was held up during the testing procedure. Each measurement setup yielded 3 base channels, 16 air and 12 movable channels. The ambient vibration was simultaneously recorded for 120 seconds, which resulting in around 500,000 data points per data set. Here is presented comparison of transversal channels for one measurement setup. On this slide, measurement on base station 16R is presented. And on this slide, measurement on movable station is presented. In the table, the dominant frequencies measured at measuring points of the upstream bridge are presented. From the results presented in the table, it can be seen that the dominant frequencies of vibration of the superstructure measuring points are in range from 1.28 to 2.92 Hz. The software Artemis extractor was used to perform the modal identification of the structure. Before procedure of modal identification, it is important to validate all channels. On this slide, singular values of spectral density matrices for single degree of freedom systems is presented. Here is presented average of all spectral densities. And on the next slide, stabilization diagram of estimated state space model. On this slide, natural frequency and damping ratio for first vertical mode are presented. And here is presented the first transverse mode. Then a natural frequency and damping ratio for second vertical mode, and for second transverse mode. The mathematical model AM3 was created using the finite elements with the SUB 2000. As the complete bridge structure was executed as monolithic structure, the superstructure and the substructure were modeled as integrated structure. The superstructure was modeled as a shell element and the piers as elastic beam elements, as this approach provides effective stiffness and mass distribution characteristics of the bridge. The pier's soil contact was modeled as a stiff support. In this slide, mathematically identified first vertical mode shape is presented. And here is the second transverse mode shape. The scope of the research was the comparison of the model parameters identified by ambient vibration measurement and model AM3. The comparison was made for the first vertical, second vertical, first transverse and second transverse modes. Experimentally and mathematically identified modal frequencies are presented below the figure. The following slides show mode shapes obtained by ambient vibration measurement and by numerical models. You can see first vertical mode shapes, first transverse mode shapes, second vertical mode shapes, and second transverse mode shapes. When the mathematically and experimentally identified modes are compared with each other, it is seen that there is a very good agreement between natural frequencies of first modes. Also, there is a good agreement between first vertical, first transverse, and second vertical mode shapes. The larger deviation was identified between the experimentally identified and mathematically predicted second transverse mode shapes. For the exact definition of obtained deviations, detailed investigation is necessary. The reasons could be boundary conditions, geometrical and mathematical properties assumptions, and eventually unexpected channel errors. The third case study is the cable stayed bridge in Tuzla, Bosnia and Herzegovina. This case study is interesting because short tower is designed due to urban conditions, which resulted in a small angle of the first and the second cable. Consequently, during the construction, increased deflections appeared in the part of the structure supported by two mentioned cables. The overpass is used for crossing pedestrians and vehicles over the city streets in Tuzla. It was designed and constructed as the cable-stayed bridge. The cross-section of the bridge consists of two traffic lanes 6 meters width and pedestrian lane. The total width of the bridge is 14.6 meters. The bridge span is 32 meters. Superstructure consists of two main prestressed beams and composite bridge deck. Composite bridge deck consists of concrete slab with variable thickness 16 to 36 cm, which is coupled with steel I-beams with 3.25 meter grid. Main prestressed beams are hanged on 4 cables. The primary load-bearing structure consists of reinforcing concrete tower, cables and steel ties. Reinforcing concrete tower is 9.5 meter height. Cables for supporting main prestressed beams are with diameter 60 mm, the first and second cable, and diameter 80 mm, the third and the fourth cable. Steel ties with a counterweight concrete block consist of 20 rebar with diameter 32 mm on one tower. Bridge testing and ambient testing were performed due to determine the behavior of cable stayed overpass for service conditions. In this slide, arrangement of measuring points is shown. Ambient vibration test was made using 0.5 G accelerometer sensors. Operating frequency range of used accelerometer is 0.5 to 500 Hz with acceleration range 0.5 G and resolution 0.00025 G. One accelerometer was used for the reference point stationary point 1, while the remaining 2 accelerometers moved to individual measuring points 2 to 22 according to the arrangement. Normal traffic flow was permitted during the testing procedure. The ambient vibration was simultaneously recorded for 120 seconds, resulting in 500,000 data points per data set. In this slide, the results of the measurements frequency spectrums are presented. The dominant frequencies of vibration of the superstructure measuring points are in range from 2.5 to 6.5 Hz. The software Artemis Extractor was used to perform the modal identification of the structure. And before procedure of modal identification, you have to validate all measured channels. On this slide, average of all spectral densities is presented. And on this slide, singular values of spectral density matrices for single degree of freedom systems is presented. Here is presented natural frequency and damping ratio for first vertical mode shape. Then for second vertical mode shape. The first and the second modes obtained using the frequency domain decomposition method, and the first mode has frequency 2.719 Hz and the second 6.79 Hz. The mathematical model, marked AM4, was created using the finite elements. The deck was modeled as a shell element. Main prestressed beams and steel I-beams were modeled as an elastic beam elements and cables as a ties. Material property was modeled based on the design parameter. The piers saw contact was modeled as a stiff support. Here you can see mathematically identified first and second mode shapes. The comparison was made for the first mode and the second mode. Experimentally and mathematically identified model frequencies are presented in table below the figure. The ambient vibration measurement was performed a year after construction of the bridge, when the mathematically model AM4 and the experimentally identified modes are compared. It is seen that there is a very good agreement between modes. The difference of natural frequencies obtained by ambient vibration measurement and by model AM4 is 4%. Since the bridge is new, the mentioned value can be attributed to the geometry simplification in modeling of the tower and uncertainty in the designed material properties of structure elements. The following slides show mode shapes obtained by ambient vibration measurements and numerical models. You can see first vertical mode shapes and the second vertical mode shapes. The presented studies show that the signal analysis of ambient vibration records allows the determination of the dynamic characteristics of the bridge. In addition, the frequency and associated modes of vibration can be assessed with adequate mathematical model. The presented results clearly indicate the great potential that ambient vibration measurements hold for monitoring bridge structures. The data collected during the ambient vibration test, which only took some hours and very few resources, processed with adequate algorithms, provided very useful information. The comparisons presented in the case studies constitute a validation of the developed mathematical models and at the same time permit some fine-tuning, especially concerning the boundary conditions and unexpected channel errors. In particular, these slides clearly show that it was possible to extract a lot of useful information from data collected during the ambient vibration test. That's all, folks. Thank you for your attention. You can contact me at university email.